So this is 9.2.3, and we're given, it's actually rated a blue square or just a normal square in the homework, but I think it's a diamond, just of how difficult the computation itself can be, more and more how annoying it can be. Not too difficult if you can crunch calculus, but given that x is a uniform, we're just asked to find the MGF phi x of s, and we use that to calculate the first and second movements. So to start off, we will use the PDF. I've written that here already. And now to grab the MGF, we simply integrate with the PDF times the kind of term e to the sx, and then integrating over dx. So this quantity turns out to be 1 over s times the quantity b minus a e to the sb minus e to the sa. So there we have it. Not too bad. But now we're asked to find the first and second moments. So obviously we could potentially just do that directly here, but this is a calculus practice. So how do you get the first and second moments? Well, you have to take the integral of phi in terms of s, and then evaluate it at 0. So differentiating gives us a pretty long expression, s times the quantity, be to b. And you should try this first. So I'm just going to kind of write down my answers, but this is like an exercise in calculus. So I encourage you review how to do this, because you have to use things like product rule and chain rule, and it's all very good practice. So this entire thing is over s squared times b minus a. Oh, of course you have to use some of the quotient rule here, right? Because we have s in the denominator. And we look at this and we evaluate it at 0, but then it does not work because you have s's. The numerator turns out to be 0 and the denominator turns out to be 0, so it's 0 over 0. What do? Well, we have to use L'Hopital's rule. That's right. You have to once again integrate, or not integrate, differentiate. So, once again we differentiate, and on top of that we have to take the limit. So we take the limit as s approaches 0, and then we get this kind of expression. It's a huge expression, so I'm just going to kind of skip towards kind of the final step, which is b squared e to the bs minus a squared e to the as over 2 times the quantity b minus a. And of course, as s approaches 0, these e's go to 1. So it's just b squared minus a squared divided by 2 times b minus a, but this is the difference of squares, and we can factor out a b minus a to get simply the sum of a plus b over 2. So wow, this is just already what we know. We know that the expected value of a uniform is a plus b over 2, but we use this kind of complicated process to solve for it. And that's only the first moment, right? We haven't done the second moment yet. So, the second moment is kind of just as bad, if not worse, because guess what? You need to differentiate once more time based on the first moment. So the second moment here is this, right? It's taking the derivative again. So hopefully you have the first part copied down, and if you didn't, review the notes or the solutions. So it's s squared times b squared e to the bs minus a squared to the e to the as and then we're going to subtract kind of 2s times kind of the similar form but with only one in coefficients, and then there's another term. Oh my god, I'm going to have to, this is still part of the numerator, plus 2 BEBS minus AEAS, and this whole thing is over s cubed and the difference b minus a. So fortunately that the first and the bottom cancel out, and then again we have to use L'Hopital's rule because you have to evaluate, oh there's the ant, you have to evaluate at 0, but the answer, so you take the limit as s goes to 0, the answer just comes out to be b squared plus ab plus a squared over 3, which is actually, you can verify that using your normal methods.